Alright, in this example we have x squared times ln of x. And your first instinct may be to let u equal x squared because you're saying, hey, that's pretty easy to take the derivative of. And maybe I'll let v equal natural log of x, dv, natural log of x dx. But the problem arises when you try to take the integral of dv to get v, and we are really not sure what the integral of ln of x is. However, we are pretty knowledgeable about what the derivative of ln of x is. It is just 1 over x. So perhaps we should switch this around, and we will now let u equal natural log of x, and we're going to let dv equal x squared dx. All right? Because we can actually integrate x squared and we can take the derivative of the natural log of x. So we're good shape. So du is equal to 1 over x dx, and v is going to be the integral of dv, which is going to give us x cubed over 3. All right, and so now we are ready to plug it into our integration by parts theorem here, which is uv minus the integral of v du. So uv is going to be the product of this and that. All right, so uv is going to be x cubed times the natural log of x over 3 minus the integral of v du. Well, v is just going to be x cubed over 3, and du is 1 over x dx. So this is going to cancel with one of those, leaving us with an integral. So I'm going to write the whole thing again. An integral of, and I'll take the 1/3 out in front, and that's going to give us a simple integral of x squared dx, which we can integrate, and that's going to be x cubed over 3. But we have a 3 out front, so that's going to make it 9. So our final answer is going to be x cubed natural log of x over 3 minus x cubed over 9 plus a constant. And that is our final answer to this problem. Alright, in this third example we have actually a definite integral this time because we are integrating from 0 to 1. So we're going to get some sort of numerical answer after we go through the process. You may look at this initially and think that you don't have the product of two functions because it's just arc sine of x. Matter of fact, to make it a little clearer, I'm just going to rewrite this as the inverse sine of x. So that way we won't get confused here. So we are integrating from 0 to 1 of the inverse sine of x dx. Alright, so you actually do have a product of 2 because if you multiply, if you just think of this as 1 times the inverse sine of x dx, you'll see that you actually have two functions multiplied. Now, once again, you have a couple of choices. Obviously, we have our little sheet right here that lets us know that when we have integrals in this form involving inverse sine, we probably need to let u equal the inverse sine of x. But let's suppose we didn't have that, and you maybe you said I'm going to let u or let's say dv equal. So let's say you said I'm going to let dv equal inverse sine of x dx. But then you try to integrate that and you say, well, wait a second, I know what the derivative of the inverse sine of x is, but I'm not quite sure what the integral of inverse sine of x is. And that's where you get stuck and you realize, okay, maybe that's not the right way to go for this problem. Maybe I should let u equal the inverse sine of x, which is what we're going to do. So let u equal the inverse sine of x, and then we're going to let dv actually equal 1 dx. Alright, so now let's go ahead and do this. So du is equal to the derivative of the inverse sine of x, which we know is 1 over the square root of 1 minus x squared dx. And the integral of v, dv, would be the integral of 1. So v would simply be x. And so now we can plug into our integration by parts formula right here. And we end up getting u times v. So that's going to be x inverse sine of x minus the integral of v, which is x, du, which is 1 over the square root, so I'm going to write it as 1 minus x squared dx. And don't forget, we've got our upper and lower limits that we have to plug in, so we have 0 to 1 here, and here we're already done with this part of integration, so we just need to plug in our 0 to 1 limit after we integrate. So matter of fact, let's do that now. If we plug in our upper limit of 1, we end up getting 1 times the inverse sine of 1. And so now you have to think backwards because it's an inverse function. What angle on the unit circle has a sine value or a y value of 1? That's going to be on the north part of the unit circle. That's going to be pi over 2. But then when you plug in your lower limit of 0, we recognize that 0 times anything is just 0, so we really don't have anything that we get from the lower limit. So pi over 2 is going to be the one part of our answer. Now we need to actually integrate this piece over here, and we can see that we can use a u substitution, and we learned that a couple lessons ago. So we're going to let u equal 1 minus x squared, and du is going to equal negative 2x dx. And so then we have du over negative 2x equals dx. So we're going to go ahead and replace everything in terms of u's. And so we're going to have x over the square root of u times dx, which is going to be du over negative 2x, and the x's are going to cancel. And I'm going to take the negative 2 out in front of the integral. Now, be careful here. We already have a negative right there, and we have a negative right there. So when you take the negative 2 out, it's going to combine with this negative and make it positive, and the 2 is on the bottom, so it's going to actually be a 1/2, a positive 1/2 in front there. And we are going to bring the u to the half up, so that's going to be u to the negative 1/2. And we're still integrating from 0 to 1. And if we integrate that, that's just going to give us 2u to the positive 1/2. And that 2 right there is going to cancel with that 2. And we have u to the half integrating from 0 to 1. And don't forget, u is 1 minus x squared. And so we have really the square root of 1 minus x squared. And so we plug in our upper limit of 1, and 1 minus 1 gives us 0. Plug in our lower limit of 0, and we end up getting the square root of 1. So our final answer is going to be, and it's all over the place, it's going to be pi over 2 from that first part down here minus 1. All right, this next problem, we're going to see that we're going to have to use integration by parts twice. And once again, let me continue to remind you, when you take the AP exam, you will be able to quickly identify when you need to use integration by parts. Clearly, it's not a u substitution problem. Once again, let me repeat that. Because if you let u equal x squared, the derivative of that is not going to cancel out sine of x. If you let u equal sine of x, The derivative of that is cosine x. That is not going to cancel out x squared. So it's not a simple u substitution problem. All right, it's going to be an integration by parts problem. And once again, the clue that you want to look for is when you see the product of an algebraic function like x squared or x or 2x or x cubed and a transcendental function like natural log, sine of x, e to the x, all right, inverse sine, inverse tangent, one of those. All right, so that's when you know that it's going to be an integration by parts problem. Now sometimes you have to use integration by parts multiple times in order to get the answer. And here is an example of that. So we are going to look at our little cheat sheet here, and we see that it fits under this category right here. And we have x to the n times sine of ax. So it tells us that normally it's good to let u equal the x part and dv equal the other part. So we'll follow that example. So u we're going to let equal x squared, and dv we're going to let that equal sine of x dx. And we're going to take the derivative of u, which is going to give us 2x dx. And we're going to integrate dv, and that's going to give us negative cosine. Don't forget the derivative of sine is cosine, but the integral of sine is negative cosine of x. All right. So now we're going to plug it into our integration by parts formula right there. And we're going to get u times v. So that's going to be negative x squared. So negative x squared cosine of x minus the integral of v du. Now I like these because you have a negative there and a negative there. And so those are just going to cancel out and give me a positive. But for now I'm going to write it out as negative cosine of x du, which is 2x dx. All right, and so let's just clean this up a little bit. So it's going to be negative x squared cosine of x plus the integral of 2x cosine of x dx. All right, you see that didn't get us very far here, so now we've got to actually use the integration by parts theorem a second time. So we need to use it on this part right here. So we're going to let, once again, go through the same process. We're going to let u equal 2x. We're going to let dv equal cosine of x dx. And so then du is going to be now 2 dx. And v, after we integrate cosine x, is simply going to be sine of x. All right. And once again, how did we know we needed to repeat it? Well, because when we look at this integral, it's not something that we can integrate. It's not an antiderivative. It's not something that we can use a power rule for or anything, so we have no choice but to use integration by parts. So let's go through the process again. So u times v is going to be 2x sine of x minus the integral of v, which is sine of x, du, which is 2 dx. So we're in good shape now because now this is something that we can integrate pretty easily. And so let's go ahead and do that. First, let's make sure we don't forget about that part. So we're going to bring that all the way down, and that's going to be negative x squared cosine of x and plus 2x sine of x. And then if we integrate sine of x, once again, we get negative cosine of x. And so that negative is going to change this negative in front of the integral to a positive. And so that's going to end up giving us positive 2 cosine of x. And once again, this is an indefinite integral, so you need a plus c on your answer, and that is the answer for this problem. Alright guys, a couple more examples, so hang on in there. This one can be really confusing, so I'm going to try to take it slow, make sure we all understand how to do this problem. Alright, once again, we've got actually we have the product of two transcendental functions, a trig function and an exponential function, and so we know for sure we need to use integration by parts. Alright, so I don't have it on the screen, but if you go to your little suggestion sheet, you'll see that they suggest that we let u equal the trig part this time. So we're going to let u equal cosine of 2x, and we're going to let dv equal e to the x dx. And so we'll go ahead and take the derivative, and the derivative of cosine is negative sine, but we have a chain rule situation, so we have to multiply by the derivative of 2x. So this is going to be negative 2 sine of 2x, and the integral of e to the x is just e to the x. So if we go through the process, we're going to say, and I'm going to put this here, you'll see why in just a moment, the integral of e to the x cosine of 2x dx is equal to uv minus the integral of v du. So uv, so that's going to be e to the x cosine of 2x minus the integral of v du. And v is e to the x, and du is negative 2 sine of 2x. So actually the negative right here and the negative right there are going to cancel. So I'm just going to make this a plus, and I'm going to put the 2 outside the integral, and I'm going to have e to the x sine of 2x dx. And then I'm going to integrate this part again using the integration by parts. Alright, so I'm going to rewrite this integral of e to the x cosine of 2x dx is equal to e to the x cosine of 2x plus, and we have to go through the process here, so it's going to be 2 times bracket uv minus the integral of v du. So I'm going to let u equal the trig part again, so that's going to be u is equal to sine of 2x, and I'm going to let dv equal the exponential part, e to the x dx, and so du is going to be chain rule again, 2 cosine of 2x, and the integral of e to the x for v is going to be the same as before, e to the x. And so we have uv, which is going to be e to the x sine of 2x minus the integral of v du. v is e to the x, and du is 2 cosine 2x. I'm going to put the 2 out there, and it's going to be cosine of 2x dx. And at this point you realize something that, well, I'll tell you what, before we do that, let's distribute the 2 inside here, and so that's going to give us 2e to the x sine of 2x minus 4 the integral of e to the x cosine of 2x dx. And I'll just go ahead and rewrite this part also, e to the x cosine of 2x. Okay, and so we realize that this part here is the same, actually with the integral, is the exact same integral over here. And if you don't realize that, you're going to start to go around in circles and realize that, wait a second, I'm trying to integrate e to the x cosine 2x dx, and I have the exact same integral over here on the other side. So what do you need to do? Well, you can now treat it like an algebra equation, and you can actually add 4 times this integral e to the x cosine of 2x dx to both sides. So you can actually add 4 integral of e to the x cosine of 2x dx. And just like any algebra equation, that's going to cancel. And so over here, if you notice now, we have 5 times the integral that we are looking to solve for. So it's e to the x cosine of 2x dx, and that's equal to e to the x cosine of 2x plus 2 e to the x sine of 2x. And so now we can simply divide both sides by 5. Divide by 5. And I'm going to pull out an e to the x here because it's common to both. So our final answer is the integral of e to the x cosine of 2x dx equals e to the x over 5 times cosine of 2x plus 2 sine of 2x. And we need a plus c after all of that because this is an indefinite integral. And that's how you do that problem. The clue for when you're going to need to add an integral to the other side is pretty much all the same. It's when you have an exponential function times either sine or cosine, some sort of trig function like that. All right? All right, this is the last example in the notes, and actually it's probably one of the easier problems. So if you notice here, we have natural log of x, the integral of that dx. And up to this point, you may have been wondering, what is the integral of natural log of x? I know the derivative is 1 over x, but what is the integral? And that's what we're going to prove here in this example. All right. So once again, you want to be thinking, what should I let u equal? Well, clearly we don't want to let dv equal the natural log of x, because then we would have to integrate that to get v. And that's obviously what we're trying to find in this problem, so that would not be a good choice. So instead, we're going to let u equal the natural log of x. And once again, here's another example where we have to imagine that there is a 1 in front of this natural log of x. So we're going to let dv equal 1 times dx. All right, so du is the derivative of natural log, which is 1 over x dx. And the integral of 1 is simply x, so v is going to equal x. And so what we have here is uv minus the integral of v du. And once again, that is right here. So we are going to say u times v, which is going to be x natural log of x minus the integral of v, which is x, times du, which is 1 over x dx. And nicely, these cancel, and so you have x natural log of x minus the integral of 1 dx, and the integral of 1 is simply x, and then you need a plus c after that because it's an indefinite integral, and that is integration by parts. All right, we'll practice some more tomorrow in class.